to measure treatment effects, and it is the difference between potential outcome at 1 when treated and potential outcome when it's not treated, and then take the population average of this difference. AT is it's just single numbers to summarize the treatment effects. However, when the individuals or group have different treatment effects, the just using a single mean may no longer good enough to summarize the treatment effects. So sometimes AT may be too large or too small to summarize the whole distribution of the treatment effects. So AT may oversimplify the treatment effects. In contrast, conditional error treatment effects, CATE, measure the treatment effects conditional on a set of variables. So if we look at the definition of CATE and compare it with the definition of ATE, the only difference is ATE is unconditional expectation, and CATE is conditional expectation conditional on some variables X. So CATE actually is a function of the treatment effects. We want to model how the treatment effects vary with the variable X. So it is a function of the treatment effects. So it's no longer a point, single point. In this case, so if we can measure the whole function of the treatment effects, we have a better ideas about how treatment effects are distributed among the whole population, how treatment effects varies among different subgroups, extras. Okay. So the main advantages of learning treatment effects is the following. The first of all, it improves the understanding of the treatment effects heterogeneities. We can ask different questions. The first one is, are the treatment effects really heterogeneous? We can also ask, how do the treatment effects vary with some variables? Because we have the function of the treatment effect, so we can ask, how when X changes, how treatment effects changes. The third question is, how do the treatment effects vary with some between pre-specified groups? And last, we can also say we do not know how treatment effects vary between some groups, so we want to ask data to tell us, to ask data to discover groups where the treatment effects are different. So this is the first advantage of learning CATE. The second is learning the CATE build the foundation to evaluate the treatment assignment policy. So if we implement, so what is treatment assignment policy? It's a probability between 0 and 1 to assign each individual into treatment or controls. So that is treatment assignment policies. We want to evaluate such policies. What's the value of these such policies? Okay, and if we have different candidates of different policies, we want to compare them. Which one is better? It turns out estimating CATE builds the foundation to evaluate treatment assignment policies. There are different versions of the CATE, conditional X. So depending on the definition of X, CATE help us to understand the heterogeneous treatment effects at different levels. First of all, at finite levels, if X refers to the individual characteristics, then CATE either have another name called individualized average treatment effects. So this is the finite level of treatment effects estimations. Okay, and now if X refer to a pre-specified group, so it's just an indicator. In this indicator has different levels. So X is a group. We can learn the group average treatment effects. So it is a gate. G represent group here. And finally, if the X represents some data discover group. So how data discover group? So data rank the individual average IITE, rank them and put them into the different groups. The first group have the largest IITE quantiles. Second group has second largest quantiles, extra, and then you have a data sorted group. So it is we can learn the sorted group average treatment effects. So in Stata, we have a Kate suite of commands to estimate, visualize, and to inference for treatment effects when you have in Kate. So for estimation, we have a command called Kate, okay? And for Kate, there are different scenarios we can use. The first one is Kate PO, which we estimate the IIT function using the partially out model. So PO represents partially out. We can also use Kate AIPW, which estimates the IT functions using AIPW model. Okay, and for gate, for group average treatment effects, we do the same thing as before, but we have to add an option called group specify the var name. Here, the var name is the name variable name of the group. So this command estimates the gate. And finally, if you want to estimate, the sorted group average treatment effects, you instead of specifying a var name, you specify a number of the group. So you're basically asking the data to discover to divide data into several groups, and these several groups indicators tell us what's a sorted group for the Kate. So this is for estimation. For prediction, predict the observation level IITs together with standard errors and confidence intervals. For visualization, so we can visualize the Kate at different levels. When you have IITs, okay, so basically we can estimate the IIT functions for each observations. So we have a distribution of the IITs. So Kate graph histogram will draw a histogram of the distribution of prediction of IITs. So Kate graph gate plot will plot the coefficient plot for the gate and gates. And finally, Kate graph for IITE plot will plot the IIT function itself. So IIT function, is a conditional, is this. This is the IIT function. Okay, when X is the individualized characteristics, it's a function. So IIT plot will plot that function. For inference, we have several estat commands to answer different questions. The first one is estat heterogeneity, which is a heterogeneous treatment effects test. So it tests whether treatment effects are heterogeneous or not. Estat gate test will test whether the group level treatment effects are heterogeneous or not. And estat classification is the classification analysis of the data-driven groups. So after data discover some groups, we want to learn how certain variables changes between these groups. So this is learning, how the axis changes with treatment effects. So that's like classifications. Estat ATE is the ATE for subpopulation. Estat projection is we project the IIT function into a linear space, so linear approximations of the IIT functions, and it can be interpreted as regular regressions. So give us some hint on how the effects of certain axes changes the treatment effects. Estat series is similar. It's also projections, but instead of to be linear, it's a non-parametric linear series approximations. And finally, estat policy evaluation, policy eval is a treatment assignment policy evaluation. Okay, so today's talk I will mainly talk about how to use Kate, but under the hood, actually the mechanism is pretty complicated. I would not touch details about how do we actually estimate Kate, but I want to just show you what's the building block in theory to estimate Kate. There are two building blocks. The first one is generalized random forest. So generalized random forest estimates the IT function tau x using a version of random forest which is called generalized random forest. Okay, that's foundation one. Foundation two is when we're estimating the gate or gates or policy evaluations, we are actually using double machine learning. It is for partitioning out AIPW estimators together with the cross fittings. This method has been out like since 2018, and now we can interpret this framework into estimation of Kate. So why do we need these two method building blocks? The benefits of them are the first one is using generalized random forest to estimate IIT functions allows us to estimate this function without assuming parametric assumptions. Because generalized random forest is not parametric, it's non-parametric, and also it does not suffer dimension curves as the other traditional non-parametric method. So that's why we use generalized random forest. Okay, and because we're using double machine learnings, we can allow high dimensional controls in both outcome and treatment models. And also because we allow high dimensional controls, there's some model selection going on inside the estimations. And because we use double machine learning, which is PO and AIPW estimators, these estimators turns out to be NIM orthogonal. That's another way of saying the estimator can be robust to machine learning selection bias. Okay, let's go on to talk about the first examples. Okay, the first example is explore the treatment effects, conditional error treatment effects. Suppose we want to estimate the effect of 401k eligibility on net financial assets. So 401k is a retirement saving plan in the USA. Okay, and just it promotes the companies it promotes the company to help employees to save money when they retire. And some companies offer this 401k service. Some companies does not offer this 401k service. So eligibility means whether you work in different companies, some will affect your final financial assets. Okay, and here we want to learn how these effects vary with some individual characteristics such as income, age, education, pension, and marital status. The outcome model is a set equal to the E41K, which is a 1-0 binary variables, indicating it's treated or not treated, times some function tau x. Okay, I will explain what tau x actually is later, and plus some control functions, g, x, and w. Okay, plus some error terms. So here the w is high dimensional controls. Okay, so when the 401k equal to 1, then the potential outcomes for treated is tau x plus gxw plus epsilon, right? And when E41k equal to 0, the potential outcomes for a set when it's not is in control, it's just gxw plus epsilon. Then you minus this function to this function on both sides of equations, you get the gx functions get cancelled, the epsilon function get cancelled when you take expectations. What stays there is just the tau x. And by definitions, as you see here, the tau x is just exactly the definition of IIG functions. So this tau x actually is a function of this is object of interest. We want to estimate functions. By the way, you see, I do not see any parametric assumptions on the tau x. We don't see how the tau x should be linear or whether it should look what it should like. We didn't impose any assumption on tau x. Then how do we estimate this tau x? Because the presence of the gx functions is a little annoying, so we want to get rid of it. So this is partitioning out estimator is a way to partial out these nuance functions. For example, this is basically workflows, well, in mathematical terms. Okay, this is again this is the outcome models, and this is the treatment assignment models. Okay, And if we taking conditional expectation equation 3 on both sides, on x and w, which is this, okay, epsilon disappear. All right. And notice that the conditional expectation of E41K is just f functions, okay? And on these conditional expectations, the g functions appear. And on unconditional part, the g function also appear. So we can just minus equation 3 on equation by equation 5, and this is the results. As you see here, the g function get partialed out. Okay, the g function can partial out, and what stay there is on the left hand side of the equation is a set minus the conditional expectation. It's like a prediction residues. Okay, on the right hand side, it's E41K minus f functions. It's also prediction residues for E41K, and then times tau x functions, which is our final object of interest, plus some epsilons. Okay, so now we can estimate this tau x by solving a local moment conditional moment conditions. So what's the local moment conditions is because tau x is no longer a single scalar parameters. Instead, it's a functions. So these functions uh, so the moment conditions of for tau x should depend on the value of x. Okay, so at different, so we have to find out the weights, local weights for different value of x, and then construct the moment conditions this way. And generalized random forest turns out to be a very good way to estimate the functions for both alpha x and tau x. Okay. So let's start estimating the models. The load data. This is we web use SS3. This is data from Chernobyl Hansen 2004 paper. For kate variables, so which is x variables, we define like age, education, and all the other factor variables. And we also define some controls, which is some continuous variables interact with factor variables. Okay, so kate covars, the global variable kate covar refer to x in the depth. If you might take the mapping between this stata command and to the mathematical definition, and the controls uh, refer to the x functions. No, sorry, w functions. Now we can estimate the k using k to estimate IGE functions. We call kate PO and specify the outcome variables and the kate covariates in the first parenthesis, and in the second parenthesis, we just have to, specify the treatment indicators E41K, and then we put controls into option controls. Because there's some cross-fittings going on, we need to specify RSET to make results reproducible. At the first glance of the output results, well, it turns out to be, no big difference between the traditional training effect estimation command, like G effects, okay? But however, so for example, this number, which actually is just ATE, which 8,107, we can interpret this number as regular ATEs, which is being able to work for a company which offer 401k will increase your, on average, we increase your asset by $8,107 compared with if you work in a company which do not offer the 401k services. Okay. However, this is just a summary of the IT functions. But under the hood, Kate also estimates the IT functions by the generalized random forest. But remember, there's the axis has many different values, so we cannot really put all the possible scenarios, possible value of IIT function into a table. That will be a huge tables. It's not possible. So instead, we can figure out a way to first to visualize these IIT functions. The first is we can use K-graph histogram to take a look at the IT predictions histogram, which basically show us the distributions of the IT predictions. Okay, so in this graph, it shows that this is the distribution of IT predictions. And as you see, the IT distributions has the fat red tails here. Okay, so the ATE, if you take the average of the whole distributions, the average should stay here, something around here. Okay. However, if you look at the most centered values of the distributions, which is this part, so which means the ATE possibly overestimates the treatment effects. Because this is just a visual inspection of the treatment effects. However, just looking at this histogram cannot, tell us whether treatment effects are heterogeneous or not. Even sometimes, even if the two treatments are homogeneous, the histogram also, can distribute it as a regular histogram. That's because there's some noise in data. So in order to rigorously test treatment effects are heterogeneous, we use E-stat heterogeneity. So it's a test to test the null hypothesis. The null hypothesis is treatment effects are homogeneous. Here we look at the p-values, which is about 4%. So that's so we reject the null hypothesis. In other words, the treatment effects are heterogeneous. Okay, so this is like the first step answering whether treatment effects are heterogeneous. So that will answer the first questions. Second is, after we estimating the IIT functions, which is a non-parametric, and we don't know the form of how that functions looks like. The first way to summarize that functions is we can, put that functions in if we linearly approximate that functions. What's that approximation should look like? So we'll linear approximate that functions with respect to x. So axis variables are all the K covards, as you see here. So this is the E-stat projections. First, we look at, the R squared of these projections actually is low, which is over 0.004. It's pretty low R squared, which actually means linear approximation to IT is does not have very good fit here. So that also means if you originally estimate the kit function, just interact your treatment variables with some interact with some x variables, which create linear approximation that cannot approximate the true IT function well. So this is how what this k r squared means, and also we have this coefficient which can be interpreted as the effect of variables on the ITEs when the IT can be linearly approximated. Okay, for example, here the income category 4 has the coefficient around these numbers, which is 18,355. So that actually means belonging to income categories of level 4 will impact the treatment effects by $18,355. Yeah, under the condition that the treatment effects are linearly approximated. So these numbers actually it tells us, the directions of the changes, directions of the effect of certain variables on the treatment effects. So it is interpreted as effects of the effects. So that's remember this is histogram is just give us a distribution of the IT functions. Okay, and now suppose we want to see how the IT functions looks like. Remember, kit function is where is a function depends on several depend on variables of x, and x has different several dimensions. Like we can have 2 variables, 3 variables, actuals, or more than 4 or 5 variables. So it's we cannot really draw a functions if we have more than 2 variables. If just 1 variable is two, we can draw that function into two-dimensional graph. If we have 2 variables, we have to draw it on 3-dimensional graph. If there are more than 3 variables, it's hard to visualize it. So instead, the IT plot actually, we can plot that functions by allowing 1 variable to change. At the same time, fix the values of other variables. So, for example, I want to see how do these functions looks like when education changes, when the other variables are fixed at some fixed values. By default, the contingent variables are fixed at the means, and the factor variables are fixed at the base levels. So think about, IT plot like we have a bread, okay, and we want to see IT plot is like we cut a bread in certain directions, and the surface of that cut surface is the IT plot. Okay. So what that function looks like, this is the results. So this, as we say, this function is hardly linear. At the beginning, before 12 years educations, basically the IT function stays pretty flat. Then at 12 up to 12 years and 15 years, there's a jump of treatment facts. And interestingly, after 12 years, the treatment, especially after 16 years, the treatment effects are no longer, significant. It's because the confidence intervals cover 0 here. So this graph actually tells us, these functions. So condition is still a case functions, but it's, for example, at this point, when education equal to 10, so this point, it tells us the conditional expectation of y1 minus I0 when education equal to 10, and the other variables are fixed at these values. And of course, as researchers, we can explore different version of the IIT function. We can that in essence we can cut this bread in different directions, and we can fix the other variables at different values, and to see how that function looks like. So as you see here, this treatment effect, it seems it's only between education between 12 years and 15 years, the education has some positive effects on the IGEs. Okay, and that's uh, short graph. And sometimes we want to ask different questions. Say we want to ask how the average treatment effects actually vary at the single variables of educations. Okay, so basically, we want to take expectation around these expectations of the other with the other variables. So all the other variables are conditioned out. Only the educations are stay there in the conditional expectations. So in that case, we can use E-stat series. Okay, E-stat series educations will approximate the IT function using non-parametric series as a series regressions. Okay, and this effect here actually shows the marginal effects of education on the treatment effects. So it's the marginal effects of education on the treatment effects. And we can also show the graph of the ATE over educations. So basically, it's this function is conditional expectation of y1 minus y0, just conditional on the educations. Okay. So for example, these variables, this point 10 means ATE. What's the ATE when education equal to 10? So this graph is fundamentally different from the IT plot, because IT plot in the conditional set, there's also some other variables, right? However, in the series plot, the other variable get canceled out. Get no get get take the average out. So we just have to know the what's the average effect of training effects when education equal to specific values. So in this way, we actually look at the training effect varies at different levels. At the beginning, we see IT plot that training effects varied at observation levels. Okay, and now we just zoom out and look at how training effects vary with continuous variables. Okay, that's the first examples. In second examples, we're asking how the training effects varies with some categorical variables. Okay, so that's a gate. Okay, when you have to specify option group with var name for the gate estimation. And here we're using IPW estimators for change. The first example we're using PO, and this one we're using IPW estimators. Okay, and we specify options group income cat. We want to learn how the treatment effect varies at different income levels. And this is the output. So the output here, in addition to ATE and PO means, we also have a estimate the average treatment effect at each different group levels. For example, this number 21,275 means the treatment effect when for the peoples belonging into income 4, which is like high income group. As you see, basically, except the second group, the first group, group 1, there's like the more income you have, the bigger effect the E401k on asset is. So this is basically the trend. Okay. We can visualize this trend by calling gate graph gate plot. It visualizes the gate functions. As you see, it's a upward trend. The more income you have, the more training effect it is. And we can also test whether the training effects group level average training effects are heterogeneous. To test the null hypothesis, the group average training effects are homogeneous. Okay, we basically testing this this for constant. So each income, each levels of a gate equal to each others. Again, we reject the null, so the training effects for group are indeed heterogeneous. So in these examples, we know we know we know the group variables we want to study. Here we specify group income categories, but sometimes we do not know how the treatment effect vary a specified group. So we want the data to tell us which group will have a bigger treatment effects, which group have a smaller treatment effects. Okay, so in that case, we use option group with a number, specified number. So that numbers will divide data into specific number of groups. And for each group, we can estimate the treatment effects. So here I specify option group 4. Okay, so that means I divide data into 4 groups, and the first group. So how we decide the group? The group is determined by the ITE quantiles. So we first estimate the ITEs, right? And then we classify the data by the quantiles of ITEs. The first group is first category is between 75% 75% quantile to the highest ITEs and actuals, and then you have a last group have the smallest quantiles of ITEs, which basically have the smallest ITE functions. predictions. However, we actually obtain these rankings by cross-fitting. So the way we need to use cross-fitting is because if we do not use cross-fittings, then we can always find, uh, the first group has the bigger treatment facts, the last group has the smaller treatment facts by just ranking the IT predictions. Okay, if without cross-fittings, and with cross-fittings, we can, we can uh, break we can break these orderings, make the ranking more robust to homogeneous treatment effects. In other words, if the treatment effects are really homogeneous, then even if you divide it by the quantiles, you see the group level treatment effects are roughly the same across groups. So cross-fitting is critical techniques to guarantee that we can also test the homogeneous treatment effects. So again, so higher because we use divided by the cross fittings. So higher rank does not necessarily imply higher IHEs. But in this case, it implies. In this case, examples IHE first group have bigger, HE gate. And as we see in the previous example, we can also use gate plot to visualize the trend of the estimations. So in this example, group 1 had higher ATE than the group 4. And we can also test it. So we can instead gate test to test the treatment facts difference between group 1 and 4. Okay. So again, we reject the null. So this test rejects the null hypothesis of the homogeneous gate between group 1 and 4. So people in group 1 have higher HEs than those in group 4. Okay. So that means data indeed discover groups that each group have different treatment effects. Okay. Then the question is, we want to ask, how do the people in group 1 and group 4 have different characteristics? So then that comes in classification analysis. For example, so we can ask, is the variables mean different between group 1 and 4? Okay. For example, we can ask how the percentage of owning a home differs between group 1 and 4. We can do is that classification own home. Okay. As you see here, in the first group, 85% of the people owning a home. In contrast, in group 4, only 46% of people owning a home. We can test the difference whether no, sorry, actually zeros. So this is test at different directions. Okay, when the difference for difference greater than 0 and difference does not equal to 0, the p-values are very small, so we can reject the nulls. So basically that means this difference is significant. Okay. And similarly, we can do how the people's age varies between the group 1 and 4. As you see, in the first group, the mean value of age is 45, and in the first group, the mean value of the age is 37. So it means this two table actually means, group 1 people tends to be people who are older and who are have more possible to own a home. Okay. In contrast, people in group 4 are younger and have a smaller probability of owning a home. So in these ways, data actually tells us, the characteristics of the groups such that these groups have different treatment effects. So this is like a classification. Okay, and last example 4 is in all these first three examples, we explore the treatment effects at IT levels, then we estimate gate, then we estimate gates. This is for treatment effect heterogeneity studies. And now it comes to how to use the Kate estimations to evaluate treatment assignment policies. So what is the policy values? So what is the policy? So policy actually is the probability pi I, which belongs to 1, 0, is the pre-specified treatment assignment probability for the ith observations. Okay, so pi I also refer to the policy. So then policy values of pi is average outcome in the population if you implement these policies. So pi I is when you put observation I into treated. Okay, so pi I times yi1 is a scenario for scenario when it's get treated. So y minus pi I is the probability when it's in control. Then times y0 is a potential outcome when it's not controlled. So for each observations, we have this weighted outcome. Okay, and weight depends on the pre-specified treatment assignment probabilities. And then you take the expectation over populations of this weighted outcome, and that's the value of the policy values. Okay, and it turns out that when you estimate the IIT functions, we already estimate this yi1 or yi0s. So that's why policy evaluations is closely related to the Kate functions. And this is the value for one policies. If we have two policies, we can just compute the difference between these two policies and tell us whether the difference are positive or negative. And ATE, so average treatment effects, actually is a special case of policy comparisons. So let's take examples. Think about two policies, okay? The first one, pi A, is treat everyone in the population, and pi B is treat no one in the population, okay? So what's the definition of ATE, which is expectation of y1 minus y0s, okay? And so y1 can be also written as 1 times y1 plus 0 times y0, okay? Similarly for y0, 0 times y1 and 1 times y0. So this is what? This is the first one, this term is the policy values for pi A equal to 1. And the second term is the policy values for pi B equal to 0. So ATE is a contrast of two policies. A policy treated everyone versus policy treated no one. So we can actually, show that in our computations. So here is one example. It's an example of lung transplant. So we want to study the treatment is this. The treatment is we have different, lung transplant possibilities. One is we transplant both lungs, which is a bilateral lung transplant, or we just transplant one lung. It's a single lung transplant. Okay, and outcome is the forced expiratory volume in 1 second relative to a healthy person's. Okay, and as before, we define some variables to indicate the Kate coverts and control variables. We first estimate the Kate functions. IIT using K to estimate IIT function. I won't repeat here. And you see here we report ATE here, which is 73.5. Okay. And now I want to pursue you. ATE is indeed a special case of policy evaluations. Let's create two different policies. The first one is treat everyone. So treat all equal to 1. The second policy is treat no one. So treat none equal to 0. Then if you do the computation instead policy evaluation, compare these two policies. Okay. This is value of the first policies. This is the value of treat of second policies when it treat no one. And this value is the contrast between these two policies, which turns out to be exactly same as HEs. Okay, 37.5243 and same standard errors too. Okay, so that is confirm that HE is just special case of treatment assignment policy evaluations. Okay, and now we can have more interesting hypothetical policies. So we want to compare another policy, another treatment assignment policies with the observed policies. So the observed policies actually happened in the data, which is indicated by trans type, which is which is realized by the doctor. And now suppose we have these hypothetical policies. We assign patient to bilateral lung transplant if the patient walking distance is greater than 500 meters in 6 minutes, and if the patient does not have diabetes. It's very simple rules, okay? Okay. And then we evaluate these two policies. We call STAT policy with this first policy 1, and then with the policy which actually happened in data, which also specified by trans type. It turns out these simple rules actually beat the doctor. It is it's the value of these policies. The difference between these policies positive is like 6. So this way, it's we can have different scenarios in our research designs to ask what would happen if we implement this. We can answer a question like that. Okay, so finally, I want to talk about a little the AIPW scores. Okay, that has been used. This is hidden. AIPW score is hidden in many different uses in CATE estimations. And for the first AIPW scores I want to emphasize is for both PO estimator and AIPW estimators, we can derive the AIPW scores. Okay, and these AIPW scores are essential to computational elements in the IITE estimators, especially for AIPW estimator. Okay, and then AIPW scores also essential for linear projection, which is we use STAT projection. In series of projection, we use in STAT series. In gate estimation, in gates estimation, and even in policy evaluations. Okay. So here is an example of fully interactive model. This model is underlying model for the IPW estimator. Okay, Y1, we have potential outcomes with G function G1. Y0 has potential outcome function G0s. And D is, treatment assignment models. Okay, so Y1 AIPW, so potential outcomes 1, the AIPW version of these potential outcomes is G1 function plus some error correction terms. This is the error correction terms, okay, which is augmented term, and this term also depends on inverse of the probability get treated. So it's called augmented inverse probability weighting terms. Okay. Similarly for Y0s. So the function of this, the purpose of these two actual terms is for bias corrections. If one model is correctly specified, your IPW score are still consistent estimates. So that's why we need these two, correction terms. Okay. For all the nuance functions, we can already estimate the G1 function, G0 functions, also the I function during the double machine learnings. So the tau functions, the IPW scores is just the difference between these two potential outcomes, right? Which indicate as gamma hat. This is our AIPW scores. Okay. Okay. Now for IT functions, when you're using the AIPW estimators, this gamma hat can be served as the dependent variables in a machine learning prediction problems because this is just treatment effects for observations before you're taking expectation. Okay. And tau x is the treatment effects after you're taking expectations. So this as if you regress y on certain x, but here it's just your y becomes the gamma hat and your x becomes the functions here, tau x here. Okay. And for the gate or gates, you regress the gamma hat, the AIPW scores on the group variables, and here the group variables can either be the pre-specified or the data-induced group. Similarly, for linear and series projections, we can do linear and series projections of the AIPW scores on the specified variables. And finally, for policy evaluations, instead of we can evaluate weighted mean of the AIPW versions of potential outcomes. So the AIPW score really useful throughout the computation of the case. So I want to make summaries. Time flies. Okay. So what can K do? We can use K to study treatment effects heterogeneities at different levels. Of course, it's only in cross-sectional data. We can also use Kate for policy evaluations, and because Kate using the generalized random forest GRF, so it's non-parametric, and it also allows high-dimensional controls. So so we use lasso or random forest to estimate unit functions. So it's semi-parametric in the outcome models and treatment assignment models. Or you can, if you want, you can also use parametric specifications in the IGEs. So it's like you add a linear interaction terms. But even using parametric assumption on the tau x functions, I still recommend you to use Kate instead of just using regressions, because Kate use the cross-fitting by default, and that will guard against estimation errors in the parametric assumptions. Okay, so the features that can be interesting to be added in the future is first one is how to handle the class data and panda data, and the last is how to do the optimal policy evaluations. So given the kit estimation, what's the optimal policies that can maximize values of have maximum values? Okay, this is the reference. All right. Thank you. I hope. So do you have any questions? I'm here. I can answer here now.
Yeah, thanks a lot.
Hi.
Hi. Thanks a lot for giving this presentation. It was really interesting.
Yeah, thank you.
Yeah, my wish for the future, but I don't think this is possible yet. But what I would really like in the future would be that this machine learning approach can be combined with our causal inference research designs. So,
Uh-huh.
in economics, we have this regression discontinuity design or difference in differences
Uh-huh.
or all these research designs to estimate causal effects.
Uh-huh.
Many of these exist in Stata, so it would be amazing to have this as a post-estimation command or somehow that we could combine this. That in the first stage we say we're estimating the causal effect, let's say with different differences. And then in a second step, we can estimate heterogeneous treatment effects and perhaps what you showed saying, okay, the algorithm suggests that these are characteristics of people or places that predict higher treatment effects or positive effects for some and negative for others. But, like as some kind of post-estimation command possibly.
Uh-huh. For DID, for the pan data for DID, uh if you well you know in Stata we can also already estimate the heterogeneous treatment effects for DIDs, right? When you have when the treatment effect varies with cohort.
Yeah.
So cohort is when you get treated at different times. You can do that already, right?
Yeah,
And now you want uh, go to one step further. So
yeah.
suppose you have even if you have that heterogeneity, you want to know how that treatment facts varies with certain variables x. Yeah. I don't know. So far, I don't know, any theoretical advances in these directions yet. Yeah. So because if you want to incorporate this framework, again, I think uh, you have to guard against the your model selection mistakes here, right? You have guidance and set. I think there's possibly some possible extension here, but I don't know any published work here yet. Yeah.
Yeah, it might even be even more natural to think about this in the regression discontinuity framework,
Uh-huh.
where very often this is spatial, where we say there's a spatial boundary at which we are estimating treatment effects.
Uh-huh.
And there, if you think about this boundary, for example, as a national border, let's say the border between the US and Canada,
Uh-huh.
and then the algorithm could potentially say these are places where we find larger treatment effects than in other places. So it could be geographically in that sense.
Uh-huh.
That you say in the West it's different from the East, for
Uh-huh.
example.
Yeah.
Yeah, but I agree. My main worry with all of these would be that we find a different effect because some confounding factor has a different effect. So
Yeah.
that it's just a violation of the assumption in one subsample, and that's why we find a very good effect, for example.
Uh-huh. 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 Yeah. 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 But the whole case estimations is based on unconditional unfoundness assumptions.
Yeah.
So the your effect fund here actually is after taking or you're already taking into account, um, the effect of other variables. It's just because, as you say, it's like interpreting regular regressions. You take the effect of certain x on the y's. It's just effect of x on y. You already take into account the effect of other variables. You already take them out. Okay, so case the same here. When you look at, for example, in our examples, when you do the series approximation of education on the E401k on assets, right? That affect education on the treatment facts. You already average out all the other variables. So I think the assumption here is okay. It's not violated on compoundness.
Yeah. So for us economists, it would always, we would be worried about the unobserved confounders, like intelligence, where we say
Right, right,
we can't
right,
measure it well enough to really be able
right,
to control for it.
right,
Yeah.
right. Yes, yes.
But in general, yeah.
In general,
Yeah.
yes. Then you need to find good instrument.
Yeah.
Yes, yes,
Exactly.
yes.
Yeah, there are more questions now in the audience also.
Okay.
You can just unmute yourself, I guess, and just ask.
Yeah. All right. Thank you very much.
Thank you.
Yeah, thank you for your presentation. My name is Benjamin.
Hi, Benjamin.
I want to find out how different is the cut from the marginal treatment effect model if you are only you're looking at heterogeneous effects. If you want to study heterogeneous effect, how different is the cut from the marginal treatment effect model?
From one model, can you repeat?
Marginal treatment effects. The margin,
Marginal treatment. Yeah,
yeah,
marginal.
yeah. And I want to find out also whether cut is available. It can be available on Stata-18 version.
No, I don't quite get your questions. What's your cut in the marginal treatment facts? If
Okay.
possible.
What I mean is that suppose
Uh-huh.
I'm interested in studying the heterogeneity effect or the heterogeneous effect, and I want to
Uh-huh.
find out how different is cut from the MTE, because MTE also does heterogeneous effect. So I want to know how what kind of a superior advantage does cut has over the MTE.
Sorry, I don't get it. No, can you type it down? Type down in the chat windows? Maybe I. Yeah, Benjamin, can you type it down in the chat window? I will see better because it sounds like
Yeah, that's fine. I'm typing.
yeah. All right, thank you. There, I now hear you well.
Perhaps in the meantime, also others can ask a question while Benjamin is writing his question.
Yeah.
If there are any other questions.
Yeah, so again, in this time, thank you from DPC for listening. And maybe our next webinar is on Friday, the 26th of September. It's also the webinar language will be English, and it will be tips for optimizing Stata for day-to-day use by Dr. Aziad Naqvi. And I think it will be also a very, very nice webinar.
What
So
difference?
yeah,
Okay.
the question is on.
Oh, marginal impact. Okay, I see. I see. How can it different from marginal treatment effects? Okay, so marginal treatment effects is only it's dy dx. Okay, it's only for one variables. You can only take marginal treatment of one variables, and here Kate is more general. It's more general. It's more general functions of the treatment effects. We do not assume any any functional form of the treatment of effect models. So it's not just for one single variables.
Okay, thank you. And
Yeah.
I was also asking whether the cat can be accessible on Stata 18. Through the-
Kate is only available in 19.
Okay, thank you.
Yeah. All
Perfect.
right. All right. Thank you.
So
All right. Thank you very much.
Thank you. Thank you. Thank you for coming.
are there no more questions? I think you. So thanks again to Dee. Thanks to Mr. Ripper again. I hope you enjoyed the webinar and see you soon again. Bye.
Bye.
Bye bye.
Bye.